Okay, this lesson is volumes of revolution, and what I mean by that is if we were to take a region and revolve it around a axis, we would get a solid, 3D solid. For example, if this triangle right here was revolved around the y-axis, it would sweep out space, and this space would be this cone, for example. So try to visualize that. Um, a right cone. Another example here, if we have a semicircle, we were to revolve that about the x-axis, we would have a sphere. Okay, so we know formulas. We can look these up, or we can recall them from grade 9. This one here was volume is equal to pi r squared h divided by 3. This one here was 4/3 pi r cubed. Okay, now, where did these formulas come from? Well, the techniques that you'll learn in this video, you can actually go ahead and derive these formulas. And we're going to start with some examples here. But before we do that, let me show you how we're going to go about doing this. Okay, so we have part of a curve f at x here, and it's bounded to the left by a and to the right by b. We've calculated this area before, so let me just recall what we did before. What we did was we took a rectangular area. I called this the ith rectangle, um, and the area of this rectangle was the height, which was f at x, multiplied by this width, which we call delta x. And what we did is we took an infinite number of these rectangles by shrinking delta x and increasing the number of rectangles. We got the exact area. So we did something like this. I starts at 1, goes to n, and then we took the limit as n approaches infinity. And this was xi here. And then we had this other notation right here, the integral notation here, and bounded here, a to b, f at x, dx. So that's how we calculated this area, the exact area. We're going to extend that to 3 dimensions. So if we're spinning this region about the x-axis, what will we get? Well, this ith rectangle I called will be the ith cylinder. Try to draw that. Because spinning this around, you'll get a resulting cylinder here, where the height of this cylinder is delta x. The radius is going to be your f at x, I. The ith rectangle becomes the ith cylinder. So what's the formula for calculating the volume of a cylinder? Well, it's just radius pi r squared h. So radius multiplied by r. Now r is your f at xi, and the height of the cylinder is going to be your delta x. So there you have the volume of this disc here, cylinder. Well, if we were to sum up all of the discs, starting from I equal 1 to n, and then take the limit as n approaches infinity, we get the exact volume of the solid. And I have a picture here, the solid generated by revolving this region here about the x-axis. So we do have a notation for this. So it looks like this, right? For A to B. And, oh, there's a mistake here. This should be squared. I forgot to square it. That's very important. So pi f at x squared. And you can easily forget that, just as I did there. So here's the formula for calculating these types of solids when revolving around the x-axis. We'll do some examples where we revolve around the y-axis, but we'll stick with x-axis for now. So in this slide, I'm just restating what I said here. Here you go, the pi is written to the left here of the integral sign because pi is a constant. So you can just concentrate on this part, evaluating this, and then whatever that gives you, you just multiply by pi and you'll get your volume. But don't forget to square the f at x curve. Um, so there you have it. There's your formula, and we're going to go through some examples. So if we were to take the parabola, the standard parabola y equals x squared, and let's bound it to the left by 0 and to the right by 2, if you were to spin this around the x-axis, you'd get this solid here that kind of looks like a funnel on its side. We can calculate its volume. We have a formula for it. From 0 to 2, f at x needs to be squared, so since f at x is the parabola, we're going to square that, dx. And the pi we'll just write out here. Okay, so there's your volume. You can enter this into a calculator, for instance the TI-83s or the TI Inspires, and it'll calculate the exact answer. I'm going to show you how you can do it without a calculator. So let's just simplify this a little bit here. X squared squared, the rule with this is the power of a power, you multiply the exponent, so that's x to the 4 dx. The antiderivative of x to the 4 is 1/5 x to the 5. Don't forget the pi, and that'll be evaluated from 0 to 2, so it'll be pi multiplied by 1/5 of 2 to the 5 minus 1/5 of 0 to the exponent 5, and we get 2 to the 5 is 32, so that's 32 over 5 minus 0, that's 0, and don't forget to have the pi as well. So here's the exact answer, 32 pi over 5. So what if we were to rotate a region between two curves about the x-axis? What would the solid look like? Well, it would have a hole in it, right? It'll look like this, and this region inside here would be an empty space. So this would be like the difference of two volumes. In this case, f at x is above g of x, so that would be the larger radius, and that would be the larger solid. So that should come first. That calculation would come first, and then the smaller radius would be the g of x, and you would subtract. So the calculation would be pi times this integral of f at x squared minus g of x squared. And let me show you an example. So in this example, we have a parabola here, y equals x squared plus 4. That's bounded above. Below, we'll have the horizontal line y equals 2, and we'll bound it to the left by 1 and to the right by 3. This region here, when you revolve it about the x-axis, what will it look like? Well, it kind of looks like a funnel here with a hole in it, a cylindrical hole. So we can calculate this volume here. It'll be pi multiplied by the antiderivative here. We got to set it up now. X squared plus 4 is above, so that should come first. That's the larger radius. That's x squared plus 4, and we need to square that. And we subtract the smaller radius will be this one right here, and that's just 2 squared dx. From 1 to 3. So how do you go about evaluating this? There's a couple ways. You could use technology. You can type this in and get the exact answer. If you were to do it by hand without using a calculator, I'll get you started on it. I'll show you what I would do. You would have to expand this. This is a product of itself, so x squared plus 4 multiplied by x squared plus 4. You expand that and you get x to the 4, and the middle terms, when you sum them up, will be plus 8x squared, and then 4 squared plus 16, and then minus 2 squared, so minus 4 dx. Continuing up here, pi multiply by this can simplify here, the constants. You get x to the 4 plus 8x squared plus 12 dx. So I'm going to leave this as an exercise for you to evaluate. It's just a straightforward power rule for antiderivatives here, and let me give you a chance to work that out. So you may want to pause the video, work it out, and I'll tell you what the answer is. You should get 445.2684. I didn't work out the exact answer, I just used the calculator for that. Let's carry on.